back with another video, and as we were doing before, we found the Crank-Nicholson analysis, and what we're going to do now is try to solve this as a set of linear equations. So we have this equation here, which we're going to need. Let me erase the circle here. And we have a bar now. That's not bad, but that's fine. So we have an initial t0, and we have an nt5. Let's just say 1, 2, 3, 4, 5. And we're going to say at t1 of n plus 1, so at a later time, t2 n plus 1, and t3 n plus 1, and t4 n plus 1. So we're creating a matrix here to solve this as a set of linear equations. And as we see above, there's a diagonal going across each one of 1 plus 2r for the left side of the equation. So let's draw that. So 1 plus 2r, 1 plus 2r, 1 plus 2r, and 1 plus 2r. Let's make this matrix C. And as we go back to look at the equation again, there is a negative r out in front on the left and right side. So on the earlier node and later node. So we're going to add that to each one. So left, right, left, right. And the ones that don't have it on the left and right are either at the initial or the ending. So we won't have to add one to the right, depending on the increments there. And the right side of the equation can be calculated from the initial values, since this is the previous time and not the later time. So it's essentially a vector. So as we do that, we're still assuming it goes to 4. So the left side is going to be r, as we had before, times t. This is going to be a position 2 now of n, plus 1 minus 2r at position 1, then plus r at t0. So it's this initial. And what we need to take account for is at the position at the later time, or previous time from the other node here, which would be, the previous time is going to be this. But since we're already at t0, we're just going to add an additional t0, so that the previous time is just going to be t0, the initial value. So that is going to be another TOR. And we do the same thing. So we'll just say RT3 then, RT4 then, and RT5. We don't need N since it's at the other side of the wall. Plus 1 minus 2R T2 then, plus 1 minus 2R T3 then, plus 1 minus 2R T4 then. There's going to be plus RT, 1 of n, plus RT2 and T3 then. But for this one, we're going to do the same thing as the first. Except instead of the previous value, we're going to do at the additional value of the node. So instead of previous value up here, the one that's circled, we're now going to take into account of the one there, the additional. So we just add another plus RT5, and we won't need an n since it's T5 is a known value. And we can do this so we can, this is going to turn out to be a number, so any value of delta t or delta x will give you a number of the r value. Now that we have done the matrix, we're going to apply this to the code. So let's switch it for there. let's see. So we can take all these values here, Control C, and move them down into a new area. So we'll take those, and we're going to apply a matrix now to this. So we're going to need solve banded, which I have already imported. So from SciPy, import solve banded. First thing we need to do is define the matrix of matrix A, which is going to be the left side of that equation. So A equals MP zeros, and there's going to be three parts: the main diagonal, the upper diagonal, and the lower diagonal. So 3. And what we're going to want is the internal nodes, which is 50. There's 50 total nodes, but to the left and to the right, we're not going to add those, so we subtract 2. And I believe I need a second set of parentheses here. So after that, we want the A values. So A of 1 to 0 is equal to negative R. The A of 1, so 1. So this is going to be the main diagonal here. So it's going to be 1 times 2 point. So I got to make sure everything's actually in integers. So this needs to be a point and a point up here, because that's going to be needed for solve banded. 2 times point is 1 minus 2, or is plus 2 point times R. And then for the upper one, 2 equals negative R again. So we're going to do the same thing for the B, but it's more like a vector, so I won't need, so we'll do A equals MP zeros. I forgot that up there. P dot zeros. We won't need to signify the shape since it's only going to be 1, so it's just nx minus 2. And we're going to define B, so B equals T of 2 times R plus 1 minus 2 point times R times T, T of 1 to negative, did it again, we have 1 plus, it's T negative 2, and I had the wrong, did it again, this R. So this is going to be left and right for these two, and then the node at the same position. So as we're doing this, we're going to need the nodes at initial, and at the initial and at the wall. So B of 0 and B of negative 1. So B of 0 is just going to be easy. You need the B of 0, obviously. So at the position. And we're going to need the temperature. So T at 0. And this actually should be negative 1. It shouldn't be down there. Plus T negative 1. And then once we do that, we can graph it. So let's grab this function up here so I don't have to type it out. And I'll just rename it Fig2. P Fig2 and Fig2. Shift enter. And it's saying, so this needs to be there. I'm pretty sure that's it. I'm an idiot. There's not a parentheses there. So yeah, it gives me this. Not what we wanted as of right now, because we're only getting pulling 1 and we're not iterating it, so we're getting multiple values over a period of time. But this looks good for now. And let's try solve banded and see what we get for the values there. So let's say solve banded. So let's say a 1 by 1 A, and let's pull A and B, see what we get. And this doesn't look exactly right for now, but it does give us a whole bunch of different internal node values, 68 and that, so we can live with that. And what we're going to do now is we're going to iterate the function so you can get it multiple times over the time step of 2000. So, oops, that was an accident. So we're saying for I in range of nt plus 1. Never forget. So unexpected parsing. What did I have at the top? I range of 1. Let's just do that for now. So 1. See that works. Shift enter. I don't get what's the problem, but we can just put all this back in actually. Right there. Make sure we ended it correctly. Tab. I can't ever get the B back out, so I'm just going to delete it because I don't feel like wasting my time doing that. Make sure it's ended correctly. And I believe we need to do what we did back up top too. So we indice it to 100. Control C. Come on. Control V. And we're going to do fig. Let's see. The parsing goes away. And it doesn't. So there's a parsing problem for I in range. I don't know. I'm almost for sure this is NT. And I almost forgot. We didn't account for the matrix here. So we'll add the solve banded up here. So solve banded for I in range of NT plus 1's right. So it must be this. I must have to add something down here. Since I haven't done that, so let's add fig.add.trace, Control C. Set the name. I don't know if we need lines. Delta mode. I don't think we'll need mode actually. So let's get rid of that. Shift enter. Delta T not defined. It's I times delta T because delta isn't. Delta T. I think it's this add scatter. So I might not even need the go scatter actually. Let's see. Let's see. Shift enter. And that doesn't look right. So I believe this needs to be possibly. And I forgot to solve banded. This needs to be equal to T1 -1. It should. Well, it gives me the same thing. So let's run it again from the top and see if this changes it. And yeah, this is what I want. So this is how you do the with finite difference without heat escaping. As you see, it's iterating from 100 values. Get that dip and it's going up. So thank you for listening, and this is my homework for exam 3.